All right. So I turned some music on in the background. Let me know if it's distracting. I can turn it off. It's just the, lo-fi beats to chill and relax to. So, if you hate it, I'm happy to turn it off. But in any case, today I wanted to read a paper, actually, a very famous paper. I've never read it, so this will be this is like a blind playthrough. But we'll be reading "Down with Determinants" by Sheldon Axler. So I've heard a lot about this paper, and the idea is pretty simple. Hello, hello, can't commute. I like that name. So it's a very famous paper, and I believe the point of this paper is that we pay too much attention to determinants while teaching linear algebra, and that there's a determinant-free approach. I'm not sure determinant-free, but like a less determinant-emphasized approach to teaching linear algebra. And I was curious about this paper. I wanted to read it together, in part because, to be honest with you guys, I love determinants. I think they're really fantastic. I think they're a great way to introduce yourself to a lot of interesting abstract concepts and a lot of techniques within mathematics. So I was shocked to learn a paper like this existed, although I do think the title of this paper is a little, perhaps he was like joking or exaggerating a little bit. So anyways, let's get started. So I'm assuming this paper is written for people who are already math professors, though I'll explain every word as we go. And in part, this means I'll probably have to, I might have to just give you guys a brief overview of what a determinant even is and what it does. And, what exactly is it that makes it so complicated to think about, and what would force someone to write a paper saying "down with determinants"? And once again, this is just down with determinants in terms of, I haven't read it. So I assume this is just down with determinants in terms of teaching linear algebra. What's purple and commutes? It says over check in 8484. Oh my goodness, there are a lot of jokes like this. Something about a grape? I don't know. I feel like I heard this joke when I was an undergraduate, which is a million years ago. There were still horse and buggies back then. So, anyways, yeah, let me know. But yeah, let's get started. And so as we go, I'll just explain things, anything you might not know, and I'll probably spend an abelian grape. There it is. Very good. So I'll explain determinants as I go. I assume a lot of people in the chat have just not seen or heard or thought about determinants before. And I'll try to explain what makes them so complicated. I'll try to make it easy on you with the thought in mind that apparently it is possible to just completely avoid them when teaching linear algebra, which is interesting. In any case, let's get started. So ask anyone why a square matrix of complex numbers has an eigenvalue. You'll probably get the wrong answer. Oh boy. Which goes something like this. The characteristic polynomial of a matrix, which is defined via determinants, has a root by the fundamental theorem of algebra. This root is an eigenvalue of the matrix. I gotta say, there's already a bit of an issue here in that I don't see exactly what's wrong with that. So, all right, let's keep on reading. So, One piece of advice I'll give you, and this is my biggest piece of advice when reading math papers, if something doesn't make sense, keep reading. Because usually the author will say something very soon that will make it make sense. This happened to me over and over again, where I'll get stuck on a line, and then I'll spend a day on the line, and then if I'd just gone on to read the next paragraph, it would have completely clarified the issue for me. So let's see if that still holds. So what's wrong with that answer? It depends on determinants. That's what. Determinants are difficult, non-intuitive, and often defined without motivation. As we'll see, there's a better proof, one that is simpler, clearer, provides more insight, and avoids determinants. Interesting. Okay, so this is why I was confused. I thought he was trying to say that the proof was mathematically wrong. But once again, I think the argument that's being made here is a pedagogical one. It's a bad teaching argument. So the idea is, of course, that the claim is that determinants are extremely counterintuitive. I think before we go any further, I need to talk a little bit about determinants and what they are, the approach you can take to kind of thinking about them, and yeah, I know. Yeah, of course, Brian. Like that killed me so many times, just getting stuck on a line or a paragraph and not continuing to go on. So yeah, definitely, yes. Okay, let me just open something to draw in and start talking about what exactly it is that determinants are and what makes them so complicated. So the thing is, there are three ways to kind of think about determinants, and they're all kind of insightful in their own way. They all help out in their own way. There are different properties of determinants that are all extremely powerful, and unfortunately, you can only prove a lot of them by thinking in a specific way. So it's good to have, it's good to have like all three approaches in mind. So the first bit about determinants that's like worth understanding if you're going to learn them, which of course this paper is recommending you not do immediately, but I guess I'm like flouting this advice and showing my bias, but there's a geometric intuition behind determinants, and there's like an algebraic, I'll call it formalism. So the actual formula that is used to define determinants, okay? And there's also some kind of abstract shenanigans going on. So the geometric intuition behind determinants is that, okay, well, what is a determinant? A determinant is a function that's defined on square matrices, okay? So if I give you a square matrix, which is just like an n by n array of numbers. So for example, if I give you a 3 by 3 array of numbers, I don't know, 1, 0, 1, 1, 1, 1, 1, 2, 3. This is just my randomly chosen array of numbers. Then a determinant is something that takes this square matrix and assigns it to a number, okay? So in this case, I guess the number would be 1 times 3 minus 2, which is 1. And let's see, 1 times 2 minus 1, which is 1. So I'm guessing the determinant is 1 plus 1, which is 2. Hopefully I did not get that wrong. So one thing you'll see very quickly about determinants is that they're hard to compute. I tried to pick an example with a 0 in it, though I'll explain the formula in a minute. Hold on, there's a comment. So it's worth working through right now. It's pretty tough at points. So interesting how differently the book approaches the subject. Yeah, fair. So a determinant is just a function. It is just a function that takes a square matrix and spits out a number, okay? At its base, that is what it is, okay? So one thing to keep in mind, the determinant the matrix has to be square, otherwise the determinant won't make sense. There are ways to make sense of determinant-like things for non-square matrices, and maybe we'll definitely talk about that when we talk about like differential geometry and stuff like that. But for now, you just take a square matrix, it spits out a number. That's a determinant. Now, the geometric interpretation of this number is that it's actually a volume. Okay, so it's a signed volume, by which I mean it's a volume with a sign attached to it. So let's start by saying that the determinant of a 2 by 2 matrix, let's say A, B, C, D, the determinant of this matrix is AD minus BC, okay? The claim is that this is the same as the area of the following shape. So if I take the first row and draw it as a vector, let's say this is the vector A comma B, okay? And let's say I draw the second vector, and this second vector is C comma D, okay? Now, as you do with vectors, you can make a parallelogram. You know, just draw a vector, you know, just like something parallel to the CD vector and something parallel to the AB vector. And the idea is that the volume, the n-dimensional volume, and since we're working in 2 dimensions, we're talking about a 2-dimensional volume, which is also called an area. So the area of this shape is supposedly AD minus BC. So, you know, why is this? Actually, hold on. Let me put AB at the bottom and CD at the top. I'll explain this in a minute. Okay. How do you compute the area of a parallelogram? Well, as with a lot of shapes, you can think about them kind of like as like a stack of pancakes. So if you have like a tilted stack of pancakes like this, you know, so this is like the bottom of your stack of pancakes. The idea is if you shift them via a skew, so you keep the same height, but you shift the shape via a skew, like so. So for example, if you push the whole shape this way without changing the height of the stack, like so, you will get a new shape with the same area as an original shape. You can also see this with like a deck of cards. Like if you have a deck of cards and it's like tilted this way, it'll maintain the same area if you straighten them out because it's maintaining the same height. And the neat thing about this is you can take a parallelogram and you can kind of like shift it to get a rectangle. And you know, if you have a rectangle, it's easy enough to compute the area of a rectangle, right? The area of a rectangle is just the product of its 2 sides, so that's not too bad. So we're going to apply the same idea to this parallelogram. So let's do that real quick. We would like to kind of take this parallelogram and skew it kind of in this direction. Oh, not the eraser. But we would like to skew it, let me use the red pen, in this direction so that it looks like a rectangle, and then we'll compute the area of this parallelogram by converting it to a rectangle, essentially. So how far do I need to skew it? Well, what I'm going to do is I'm going to draw the a vector perpendicular to AB. Okay, so a vector perpendicular to AB is going to be negative B comma A. This is not too hard to see. If you're familiar with dot products, you can check that the dot product of these 2 vectors is 0. That's how you know that these are perpendicular to each other. And this will basically tell us like where our stack of pancakes needs to go, like where the skewing needs to stop, right? I need to push it until it touches that vector over there, okay? Now, if you're unfamiliar with dot products, I mean, maybe you haven't seen this before, another way to see this is if you remember from your middle school algebra classes, if a line has a slope AB, then the perpendicular line will have a slope negative B over A. I think this is something that they still teach in like middle school or whatever. So there you go. So, you know, it's not too hard to see that negative BA is going to be perpendicular to AB. Okay. And so now the question is, you know, how do I push this vector CD onto negative BA? So I need to kind of push this down over here. And this is not too hard to see. The idea is, of course, that this is going to make a right triangle. Like CD, if you push it down to here, is going to make a right triangle. So we're interested in, let's see, the length of this green vector over here. So after I'm done skewing, I should get a rectangle that basically looks like this. Okay. Let me know if that makes sense, or if there are any comments about that. Okay. So, you know, you're trying to push CD down to this vector over here. How's that's going to happen? So we're going to have to do what's called a project CD down to here. Now, keep in mind that this is a right angle in here, right? So also, when I'm done pushing CD down onto this vector, it'll be a scaled version of negative B comma A. So this green vector that I'm interested in, maybe I'll use a different color for it because I've already used green now all over the picture, but let's use pink, or I guess close to lilac or something. This pink vector is the one that I'm interested in because its height will be the height of the rectangle that I'm interested in. Okay, so once again, keep in mind that this is a 90-degree angle, and also keep in mind that this pink vector is a scaled version of negative b comma a. So this pink vector is going to be some constant, I'll call it alpha, times negative b comma a, because I scale negative b comma a to get that pink vector, okay? So this vector, the one that's pointing upward, is going to be v minus p. I see. And so v minus p has to be perpendicular to w, which means the dot product between v minus p and w has to be 0. And w is just a scaled version of p. So w is just some constant alpha. P is just a scaled version of w. So you can rewrite this w. I'm talking to myself at this point, but I'll clarify this in just a moment. It's just going to be alpha times w. So we know this, and I see. So alpha is going to be v dot w over w dot w. That's exactly right. Okay, let me clarify what I said. So I'm projecting CD onto negative BA, like this picture over here. And I know this purple vector here is going to be some multiple of negative B comma A. So I'm just going to call this alpha times negative B comma A, because I know it's a scaled version of negative B comma A. Okay, but then I also know that this must be, like, if I take this vector over here, and this is the part that was confusing me. I need a new color, maybe yellow. This vector here, this yellow vector is going to be perpendicular to the purple vector. And the yellow vector is, of course, CD minus the purple vector, right? So we know that CD minus the purple vector, which is alpha negative b comma a, right, dotted with w, which is, in this case, negative b comma a, is going to have to be 0. And so what we get is that alpha must be the dot product of CD and BA divided by the dot product of BA with itself. So alpha is going to equal CD dotted with negative B comma A over negative B comma A dotted with itself. Let me know if that makes sense. And so alpha is, in fact, going to be AD minus BC over A squared plus B squared. Okay? All right. So the length of this purple vector, you can check, is going to be, from that computation, just AD minus BC. I wrote AB minus BC. So it's going to be AD minus BC over A squared plus B squared. So the length of this vector, the length of this purple segment over here, is going to be AD minus BC divided by the square root of A squared plus B squared. And the length of the bottom of the rectangle, that's this segment down here, is going to be the square root of A squared plus B squared. So when you multiply them, you get exactly AD minus BC. So that's why the area of this parallelogram is precisely going to be the determinant. Okay, I definitely fudged that one up a little bit. So let me know in the comments if what I just did there makes sense, or if you find it at least plausible that the area of this parallelogram is actually AD minus BC. Okay, well, no responses. I guess I'll just keep going and see what happens. So this is the geometric interpretation of the determinant, by the way. So you're going to get the area of the parallelogram made by the two vectors that are the rows of the matrix that you are considering. Now, one thing to keep in mind about the determinant, and this is something that I did right at the start, I swapped AB and CD. Like I put AB at the bottom and I put CD at the top. But notice if I put CD at the bottom and put AB at the top, right? So for example, if I swapped the two rows of the matrix whose determinant I'm computing. So if instead, let's say I computed the determinant of CDAB. And this would correspond to the situation where now CD is at the bottom and AB is at the top. And so in this case, the determinant would be the opposite. It would be BC minus AD. Hold on, let me write it somewhere else. I realize I'm covering myself. So the determinant of CDAB is going to instead be BC minus AD. So notice this is the negative of the original determinant. So determinants have the second additional property where if I instead swap, right? If I swap the two rows, that negates the determinant. So you might ask the question, what is actually the volume of this parallelogram? Is it AD minus BC, or is it BC minus AD? Well, whichever one is positive, right? Since one is the negative of the other, one of these numbers is going to be positive and the other number is going to be negative. And so the volume, so the area of this parallelogram is just going to be, you can just say it's the absolute value of AD minus BC. So the area of this parallelogram is just going to be whatever the absolute value of AD minus BC is. So this is the geometric interpretation of the determinant. It gives you the n-dimensional volume of the parallelepiped that's spanned by the rows of, that's created by the rows of the matrix. And by the way, this works in any dimension. So for example, let's say I were to think about the determinant of, let's say ABC, DEF, GHI. So in this case, there are three vectors. Maybe I won't draw axes. I think that might make it more confusing. So you have this vector, let's say ABC. And you have this vector, let's say DEF. And you have this third vector, let's say GHI. Just like we made a parallelogram with two vectors, we can make what's called a parallelepiped with three vectors. And it's exactly how you might think. You would do here, here connecting these dots, here. Let me erase the labeling, or let me put the labelings on the other side so the drawing makes more sense. And if you've ever, if you want some intuition behind what a parallelepiped is, just play with a box, okay? So when you get a box in the mail, it starts out looking like, the prism of a rectangle, basically, a cuboid, it's called. And so a parallelepiped is the shape that you would get when you start playing with the box and bending it along its axes. So this is what a parallelepiped looks like. Okay, hold on. There you go. That's sort of what a parallelepiped looks like. So if you draw your three vectors, you get a parallelepiped out of it. And what you'll see is that the determinant of this object is going to be the volume of this parallelepiped, but with potentially a plus or a minus attached to it. And remember, this depends on the orientation of the vectors. Now, when you first start learning about determinants, you might think that this plus or minus sign is like a nuisance, right? Maybe you're thinking, I'm just interested in the volume of this shape. I'm not interested in this sign that gets associated with it. But it turns out this sign is actually very important as well. So the thing that makes this sign important is it actually keeps track of how the vectors are oriented at the end of the day. So as I was mentioning earlier in the two-dimensional case, if I put AB at the bottom and CD at the top, I get one determinant. And if I swap their orientation, the determinant negates. Okay? So this turns out to be extremely important when you're studying orientations of more complicated shapes. So for example, one way you can tell that something like a Mobius strip is not orientable. So, if you take a Mobius strip and attempt to draw a Mobius strip. Okay. Something like that. So Brian asks, so we can always find the volume of a parallelepiped via determinant of its constituent vectors? Yes, absolutely. Absolutely, you can do that. I was mentioning that this the fact that the determinant switches signs when you swap any two vectors, or in other words, when you change the orientation of your vectors, is also important because it allows you to detect that something like a Mobius strip is not orientable, right? So you could compute determinants on one side of this, and start and keep and this would be determinant computations within like the tangent space here, and then you keep doing them as you travel all the way around, and you'll get a sign error essentially. As you try to compute determinants, like what'll happen to this tangent plane is it'll flip as you get to the other side of the Mobius strip. And so you'll get a weird like sign issue going on over here. And so I just want to point this out because I don't want you, if you're just interested in the volume of this object, in the n-dimensional volume of this object, you're not going to care about that additional plus or minus sign that you get on the outside. You would, as a Kant commute says, just take the absolute value. Right? However, the sign has its own practical applications as well. You can use it to detect that certain shapes are orientable. So for example, if you take something like a Klein bottle or rear projective space or a Mobius strip, you'll notice that determinant computations won't work consistently across the tangent spaces that you get over the entire surface, which is quite interesting. By the way, an easy way to see that you really do get, actually, I'm not sure how many people know about cross products in the chat right now, so I'm probably not going to go into it. But you'll just have to trust me, I suppose, that if you take the absolute value of the determinant, you really do get the volume of the n-dimensional parallelepiped that is made by the n vectors in the matrix. By the way, another actually really important practical implication of this, and this is part of the reason why it's brought up in linear algebra so much, is if all of your vectors don't make a parallelepiped, like let's say they just make a flat box, which will happen, for example, if one of the vectors is a linear combination of the other two, right? So let's say all three of these vectors lie on a plane, right? They're just completely flattened out. Then in this situation, you will always get that the determinant is equal to 0 because the volume of this box, the volume of this completely flattened out box in this case, is going to be 0. So funnily enough, you can use determinant as a detection device to tell if there's if one of the vectors is a linear combination of the others. Or another way to say this is if one of the vectors, or if like all of the vectors lie in a plane or a subspace that is of a smaller dimension than the entire space, which is interesting. So there's like an algebraic implication to this parallelepiped having 0 volume. Okay? All right. So that's just like a little bit of geometric intuition behind the determinant. I mean, there's so much more you can say about all of this stuff. There's also the algebraic kind of formalism of how you compute determinants. Okay, so there's two different ways people have determinants defined in their classrooms. One is a method called development by rows or columns. And the other is via permutations. And I guess I'll talk about both. And one of these days I will get back to Axler's paper. I will grant you that I didn't think that I would be explaining determinants in such detail, and I will hand it to the point of the paper is that it is a little tricky to explain. Like I'm thinking about the experience of someone seeing this for the first time in chat right now, or just like watching this video later, and I do think that they would have maybe I'm doing my best, but I do think they might have a slightly hard time parsing through all this information. It is a lot of information, but at the very least, we'll say geometrically, it's a volume of an n-dimensional parallelepiped with a plus or minus attached to it. That's also significant. And algebraically, there are two formulas. There are two algebraic formulas you can kind of use to compute determinants. One is development by rows and columns, and one is via permutations. So let me talk about development by rows and columns first. So here's how you compute a determinant by developing via rows or columns. So let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? I don't know. Let's say this is my determinant. Okay, we've already discussed what 2 by 2 determinants are, right? The determinant of the matrix ABCD is AD minus BC. Okay. Now, it turns out that there is a recursive definition you can use to continue this, to compute basically the determinant for an n by n matrix. Here's how you do it. So here's what I want you to do. Let's see. Let me erase something. Let me just give myself a little bit more room. If I give you a 3 by 3 matrix, like say 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Maybe Axler thinks it's better understood as an emergent consequence of previous knowledge. Yeah, probably. But I guess I felt like his paper might seem a little pointless if you don't know how that it is a little painful to explain determinants. So maybe watching me go through this pain is enhancing Axler's point. But let's continue. So the algebraic idea behind determinants is, okay, so let's say I give you a 3 by 3 matrix. So here's what I want you to do. I want you to put a checkerboard of signs on top of the 3 by 3 matrix. And so in the top left corner always goes a plus. Okay? And it's a checkerboard of signs. I want you to go minus, plus, minus, plus, minus, plus, minus, plus, like so. So if you were to compute the determinant of a 4 by 4 matrix, this is what the checkerboard of signs looks like. So, plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. Okay, so this is what the checkerboard of signs looks like in a for a 4 by 4 matrix, and so on. So just make sure in the top right corner there's always a plus. All right. Now here's the recursive definition. So let's keep our board up, our checkerboard. Pick your favorite row or column in this matrix. Maybe pick one with easy numbers, or especially try to pick one with a lot of zeros in it. Okay, but you can pick your favorite one. You can pick any one. So, for example, for whatever reason, I'm going to pick column 2. I don't know why. This is a random choice. It doesn't matter. You'll get the same answer either way. So the idea of teaching this method in such generality is so that you can pick like the easiest one in order to compute the determinant most effectively. So, you know, just, okay, we're picking this one. So here's what we're going to do. So it's 2, 5, and 8, right? 2 will get a minus sign. 5 will get a plus sign. 8 will get a minus sign. Hopefully that makes sense based on this this checkerboard right here. Now, 2 will get multiplied. So here's what you do. So now look at 2 and delete the row 2 is in and the column 2 is in. You'll be left over with a 2 by 2 matrix. Okay, so 4, 6, 7, 9. Okay, and next, hold on. So it's 2 times whatever the determinant of 4, 6, 7, 9 is. Okay. They do the same thing with 5. If you delete the row and the column that 5 is in, you'll be left with a 2 by 2 matrix. So then this will be the determinant of 1, 3, 7, 9. And then if you delete the row and the column that 8 is in, you'll be left with another 2 by 2 matrix, which is 1, 4, 3, 6. Now finish this up. So the determinant of 4, 9, 7, what is the determinant of this? So 9 times 4 is 36, minus 42, which is negative 6. So I believe this is a 12. And yeah, let me know if I make any computational errors. I'm definitely not the best calculator in the world. So 1 times 9 is 9, going here. And 7 times 3 is 21. So 9 minus 21 is negative 12. And negative 12 is being multiplied by 5, so you get negative 60. Okay. 1 times 6 is 6. 6 minus 12 is negative 6. Negative 6 times negative 8 is 48. Plus 48. So the determinant of this matrix is 12 minus 60 plus 48, which is 0. I wasn't expecting that. Hold on. And once again, adding to Axler's point that these computations are a bit unpleasant to do. So let me I've opened Mathematica. Let's just do the determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it is 0. Oh my goodness. I was very nervous there. So, all right, it is indeed 0. But the idea is that you could have picked whatever row and whatever column you wanted to compute the determinant. Okay, so we got 0 this way, right? Let's pick a different row. I'll let chat decide what row or column to pick here. Let me know if you want to pick row 1, row 2, row 3, or I guess column 1 or column 3, because we already did column 2. And there's a bit of a delay between what I say and what chat says, so I'll just wait a second. See if there are any strong opinions. Third row. Okay, sure. Let's do the third row. So the third row, let me erase the gigantic circle here. So this is 2, 5, 8. So the third row is 7, 8, 9. Okay. So 7 gets a plus sign, right? 8 gets a minus sign, and 9 gets a plus sign. Okay. So 7 will be multiplied by the determinant of the matrix that you get if you get rid of the row and the column that 7 is in. So that'll be 2, 3, 5, 6. Okay. 8, so this will get multiplied by the determinant of the matrix that you get if you delete the row and the column that 8 is in. So this is 1, 4, 3, 6. And 9, this is going to be determinant of 1, 2, 4, 5. Okay, so let me know if everything I've done so far makes sense. So 2 times 6 is 12. 12 minus 15 is negative 3. Negative 3 times 7 is negative 21. Okay. 1 times 6 is 6. 6 minus 12 is negative 6. Negative 6 times negative 8 is 48. Okay. 1 times 5 is 5, right? And 5 minus 8 is negative 3. Negative 3 times 9 is negative 27. Oh, what do you know? 0 again. So it really doesn't matter what row or column you pick. Okay? You can pick whatever row or column you want and just do this algorithm. And you get the same answer every time. I realize I'm covering it up, but you do get 0. So the reason I wanted to emphasize that you can use whatever row and whatever column you please is sometimes you'll be given a matrix that has like a particularly nice row or column. So for example, let's say you have this matrix. What row or column would you pick to compute the determinant of this matrix? So Kishore says the third column. That's a good choice, but there is a better choice. Second row looks juicy. It is indeed very juicy. So that's just for, you won't have to do this forever, but just for now, I like putting these like little checkerboards up just so I don't get the signs wrong. I would say the number one error computing determinants is getting the signs wrong. So notice the only thing here, so it'll be 0 times, so it's just 0. So it's like negative 0, positive 1, negative 0. But 0 times anything is just 0. So I can just completely ignore these, right? And so it's just 1 times the determinant of 2, 7, 3, 9, which will give me 18 minus 21, which is negative 3. Nice, right? So I wanted to teach it to you this way. So most of the time, so you do learn 3x3 determinants at most high schools, but most of the time they won't teach you that you can actually use whatever row and whatever column you want. And I actually think this is of great practical importance when it comes to computing determinants. Assuming Axler is not your linear algebra teacher. If he is, then I guess it wouldn't come up at all because you wouldn't be doing this until the end. So hopefully that makes sense. All right. And just so you know, this algorithm is completely recursive. Okay. So for example, if you had to compute the determinant of this matrix, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So it would be 1 times the determinant of 6, 7, 8, 10, 11, 12, 14, 15, 16. And please stop me if, yeah, Axler would vanish me. But please stop me if what I just did does not make sense, So it's 1 times the determinant of 6, 7, 8, 10, 11, 12, 14, 15, 16, but then minus 2 times the determinant of 5, 7, 8, 9, 11, 12, 13, 15, 16, and so on it goes. So this is so there'd be 2 more of these, and I hope you can see it is. If there isn't an easy row or an easy column to pick, this method is really quite nightmarish to carry through. There's 2 other ways you can compute the determinant of a matrix. I'll get to them when I talk about the abstract method, but there's another algebraic definition which turns out to have theoretical importance, and it has to do with permutations, essentially. Okay, so let's go back to our matrix, which was 1, 2, 3. 4, 5, 6, 7, 8, 9. Okay. So one way in which people define determinants, and this will seem kind of like weird, but I'm just going to write the definition down. But the one way in which people define determinants is like so. So write down all the permutations of three things. So this is a 3 by 3 matrix, right? So if this is a 3 by 3 matrix, I want you to list out all the permutations you can have of three things, okay? So the permutations of three things are, well, I can do nothing, right? So I can just write 1, 2, 3. That's one permutation of three things. I can, for example, you know, I can keep 1 the same, but I can swap 3, 2, right? And I'm also going to write the number of swaps I did in the side here. So swaps. So to get the permutation 1, 2, 3 from 1, 2, 3, I did 0 swaps. Okay. To get the permutation 1, 3, 2 from 1, 2, 3, I had to do 1 swap. Okay. To get the permutation 2, 1, 3 from 1, 2, 3, I had to do 1 swap. Does that make sense? All right. Now, to get the permutation 2, 3, 1 from 1, 2, 3, I had to do 2 swaps. I had to swap the 2, 1, and I also, when I was done, I had to swap the 1, 3. So that's 2 swaps. Okay. What about the permutation? Let's start with 3 now. So how about 3, 1, 2? So to get 3, 1, 2, I had to do 2 swaps. Okay. And then finally, there should be one more permutation, which is 3, 2, 1. To do this, I had to do, I guess, 3 swaps, because I had to swap again after I had 3, 1, 2. Let me know if this makes sense. Also, the music is a little loud for me. I'm just gonna. Okay, it does not get any. Okay. All right. So you have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. All right. Hopefully makes sense. So I just wrote down all the permutations of 1, 2, 3, and I also wrote down the number of swaps it took to get to that particular permutation. Okay. So here's what we're going to do. In the matrix, I'm going to take So I'm going to take the 1, 1 entry, the 2, 2 entry, and the 3, 3 entry. Okay. So I'm always using you know, let's say row 1, row 2, row 3. Okay. And in row 1, I'm using entry 1. So that's 1, right? In row 2, I'm using entry 2, which in this case is a 5. In row 3, I'm using entry 3, which in this case is a 9. Hopefully that makes sense so far. For the next one, in row 1, I'm using entry 1, which is a 1. And in row 2, I'm using entry 3, which is an 8, right? In row 3, I'm using entry 2, which is a 6. In row 1, I'm using entry 1, which is a 1. In row 2, I'm using entry 3. Oh yeah, no, it's fine, which is a 6. And in row 3, I'm using entry 2, which is an 8. Okay. Then in row 1, I'm using entry 2, which is a 2. And in row 2, I'm using entry 1, which is a 4. And then in row 3, I'm using entry 3, which is a 9. Okay? And you just keep doing this. I'm not going to... This is a very labor-intensive process, but I swear it has a lot of... the last one with only 1 swap, 1, 3. It's like consecutive swaps, not like... Yeah, you can only swap adjacents. That's exactly right. And so I'm not going to bother finishing this. I'll leave this to you as a homework exercise, but it's just another way to think about, this is an extremely algebraic definition of a determinant. And the nice thing about this one is you can easily prove. So the theoretical issue you might think with the original definition is, how come it doesn't really matter what row or what column you use? And the nice thing about this definition is that there's only one, and it's actually not hard to show that all the row and column stuff that we did is actually always equal to this definition. There's one more thing we need to do. So the idea is you need to multiply these numbers together, like so. And then the sign they get is 1 if you use an even number of swaps, and -1 if they use an odd number of swaps. So this would be negative, negative, and you just have to trust that if you multiply these numbers and add them all out, you will get the same determinant that we've been computing this whole time. So this is another way to think about determinants. And I'll stress again, the more ways you have to think about something, the easier your life will be, because there are going to be some properties or some things or some ideas that are going to be trivial to prove if you think about it one way, but like impossible to prove if you think about it another way. So I'm just trying to fill you up with as much, with like as many ideas and ways of thinking about the determinant as possible. So let me know if this way of computing determinants makes sense. All right, I'll wait for you guys to respond, and then I want to talk about the abstract definition of determinants as well. Okay. If you think about determinants in an abstract way, what is like an abstract definition of determinants? Okay, so a determinant will take in an n by n matrix, right? And it'll give you a number at the end of the day, right? You take a determinant of an n by n matrix, and it'll give you a number. Here's how I want you to think about this. So every n by n matrix has n. So Can't Commute says it's a fine definition, but I don't know if it makes intuitive sense to me. So if you, for example, recursively keep expanding by the first row, you'll see that that sign chart I made about the swaps corresponds, like that checkerboard of signs corresponds precisely to how I'm assigning signs via swaps. And you'll also notice that every product for a permutation will happen exactly once. So you can check if you develop along any row or any column, you'll be doing precisely n factorial products. And the signs that those products will have will be precisely the same as the ones that I made in the table. So I realize I'm not proving anything, though. I mean, if you really want me to, I could do that. I just don't feel like it would be particularly instructive. Also, one of these days we need to get to the essay that I said I was going to read. But I want you guys to have like a reasonable idea of what a determinant is. So now we're on the abstract ideas. So okay, so you have geometric, you have algebraic. Let's talk about the abstract idea of a determinant. So determinants, n by n matrix, you'll have n columns here, right? Just n columns in here. So here's what I want you to think about. You can think of abstractly as a determinant is a function of these n vectors. So you can call this one like v1, you can call this one v2, you can call this one like v3, and all the way to vn. So instead of thinking of it as a function of n by n matrices, you can instead think about it as a function of n vectors that sit in Rn, and it assigns these n vectors to a real number, or I guess a number. You don't even have to use. Brian says, noticed almost all structural algebraic definitions are not the most intuitive at first, but they're so useful for actually proving theorems, lemmas, etc. You said it, man. You said it. That's absolutely true. In general, I think it's just good to just have as many definitions as possible of something. I think even before reading Axler's paper, that would be like my going in objection to it. I'm more than willing to have him change my mind. Like, that's perfectly fine. But I've gotten a lot of value in my life personally by knowing about determinants. And I'm happy that I spent a lot of time on them, you know. They've definitely made my life easier proving things. So I am curious. I'm curious what he has to say about that. But let me finish this. So instead of thinking of determinants as a function of square matrices to numbers, you can instead think about them as like a function that takes n vectors in, let's say, Rn to a number. Hopefully that makes sense. Now, if so, the determinant is actually the unique function that is multilinear. So when I say multilinear, what I mean to say is, if you, for example, take the determinant of like a bunch of vectors, like, you have a vector in here, so that's the first column of the matrix, and you just keep on going, right? And in the middle here is the linear combination of two vectors. So let's say v plus bw, like so. And then you just keep on going all the way to the end. This will always split as the determinant of like a times the determinant of v1 and then v all the way to vn, plus b times the determinant of same thing, v1 and then w all the way through vn. Also, I realize I'm probably going to cover myself, so let me try and move myself here. Hopefully what I just did there makes sense. I realize it's a little complicated, but if you have a linear combination of two vectors as one of your columns, like if you take like a times one vector plus b times another vector, this is kind of like an amazing and powerful property of determinants. It always splits up like that. Okay, so determinants are multilinear in that way. So if one of your columns in your matrix is the linear combination of two, you can split that out. You can kind of distribute that out over two separate determinants. It's kind of insane, right? So Can't Commute says I like this definition a lot more. You will, certainly. I like this definition the most too. But let me make sure I actually finish it. Another property of this is that it's anti-symmetric. Okay, anti-symmetric. So if you swap two columns of the matrix, let's say, so if you swap two columns of the matrix, that will negate the determinant. Brian asks, does this work for arbitrary amounts of vectors? Yes. Make sure your matrix is square, obviously. You can only compute determinants for square matrices, but yeah, absolutely. You can have 1,000 by 1,000 matrix, and if, say, the third column of that matrix is a linear combination of two, the determinants will split up like that. Okay? So determinants are also anti-symmetric. Okay? So in other words, the determinant, if you swap two columns, that always negates the determinant. So for example, like v1 through, let's say like, you have vi somewhere here and then vj somewhere here all the way through vn. And let's say you swap them. Okay, and this time I don't mean adjacent swaps. I mean arbitrary swaps. You can swap vj and vi. This will be negative the determinant of v1 through vj, comma vi, vn. Okay, so if you swap two columns, they don't have to be adjacent. That will negate the determinant. Okay, this should remind you a little bit of what we did originally with the parallelogram. Notice when we swapped the top vertex and the bottom vertex, what happened was the determinant negated, right? And it turns out this is true in any dimension. If you swap any two vectors, the determinant is negated. Okay, so determinant is a function that sends n vectors in Rn to a number that is multilinear and anti-symmetric. Multilinear means it's linear in each column. Anti-symmetric means if you swap any two of the columns, you will always get negative of what you originally started with. Okay? That's another thing. The final property of determinants is that it's normalized. So okay. Normalized in the sense of if you compute the determinant of the identity of like the standard basis vectors, so you know, like 1, 0, all the way down to 0, 0, 1, 0, all the way down to 0, and then 0, 0, 1, all the way down, you will get 1. Okay, so this is the final property of determinants in that if you compute the determinant of the standard basis vectors, usually, expressed as usual, you'll always get 1. Okay, it turns out the determinant is the only function with all three of these properties. Okay, that's kind of wild. So this is like the super duper abstract definition. Okay, it's very not intuitive, but the determinant is the unique function that has all three of these properties. There's only one function out there that has 3 properties, and determinant is it. The determinant is it. So yes, normalization removes the arbitrary constant. Now, this one's kind of interesting. So for example, let's say you wanted to prove one of the most famous properties that determinants have, which is that the determinant of the product of 2 matrices is the product of the determinants. Okay, so if you wanted to prove that the determinant of the product of 2 matrices is the product of their determinants, you wanted to do it geometrically, good luck. What does the parallel piped look like when you multiply the 2 matrices? Honestly, I have no idea. I don't know. I don't think anyone knows. Well, actually, that's a strong statement. But I've never seen, I've read a lot of linear algebra books in my day. I don't know what the product parallel piped would look like. So, gone. Now, I've given you a couple of algebraic definitions for determinant, but once again, pain is all I see if you attempted to use any of them to prove this, okay? But if you trust the abstract definition, okay, here's what I'll do. Using the abstract definition, remember, the abstract definition is that the determinant is the unique function that has these 3 properties, right? There's only one function with these 3 properties. Its name is determinant. Determinant is the unique function with these 3 properties. Using that, it's so easy to prove this. Watch. Okay. There are 2 cases, okay? Case 1 is if number 1, if one of these 2 numbers is 0, it's not too hard to prove. So for example, if the determinant of A is 0 or the determinant of B is 0, it's not hard to check the determinant of A times B is 0. And in fact, you can even check it geometrically, right? So if you, for example, multiply A with a B, right? Then if B has a determinant of 0, then all of the columns of B will be contained in some like subspace. And then all of the columns of A times B will also be contained inside some lower dimensional space. So you'll get a flat box and you'll get the determinant of 0 on both sides. There's a little bit more work to do there, but it does require a little bit of linear algebra, and I don't want to get into it right now. But I guess you'll just have to trust me that if one side of this equation is 0, it's not very hard to check using some basic linear algebra that both sides of this equation are going to be 0. Okay? What if both sides of this equation are not 0, right? Okay. Here's what I'm going to do. This is what I'm trying to show. I'm trying to show that the determinant of A times B is equal to the determinant of A times the... Oh, hello, John. I'm trying to show that the determinant of A times B is equal to the determinant of A times the determinant of B. Okay? Here's what I'm going to do. I'm going to define the following function. I'm going to define the determinant of A times B divided by the determinant of A. So that's my function. This is a number, right? I'm going to define a new function. I'm going to call it I don't know. I won't call it a determinant. I'll call it a schmeterminant or something. I don't know. But it's a function that takes b, and instead of mapping it to the determinant of b, it maps it to this number. Okay? So I have two functions. So I have b. Oh, hold on. Let me move my face so you can see what I'm doing. So here's my function b. It maps to the determinant of a times b divided by the determinant of a. And then I have a second function, b, that maps b to its determinant. Okay? So, hold on. Hitoshi has a comment. Abstract 1 is more intuitive than algebraic for me. For instance, the 1, 0, 0 column is times larger than geometry volume is a times larger. Yeah. Okay. I'm happy. I'm happy people like the abstract definition. Okay. So, you know, this is a function calling it the schmeterminant, and this is a function calling it the determinant. But remember, there is only one function. You have to check this, but it's true. There is only one function that's multilinear, that's antisymmetric, and that's normalized, that maps matrices to numbers. And you can check, it's not too hard to check, that both of these functions are going to have those properties. Okay? So it turns out both of these functions must equal one another. So you get the determinant of a times b over the determinant of a equals the determinant of b, which proves the theorem, which is kind of insane. I mean, this is like, I mean, it's just the power of thinking abstractly, right? So doing this geometrically is a nightmare. Doing this algebraically is a nightmare. But if you have a little bit of background, using the abstract definition of determinant, if you really do believe that there's only one function that's multilinear, that's antisymmetric, and that's normalized, you can check both of these are multilinear, antisymmetric, and normalized. They both must be the same thing. So the determinant of a times b over the determinant of a is equal to the determinant of b, which gives you that the determinant of a times b is equal to the determinant of a times b. See, abstraction. Nice, right? It's quite interesting. Let me tell you something else. This abstraction also allows us to more easily compute determinants. Okay? So I'm going to give you another formula to compute determinants. This is really interesting. So let's say you have a matrix that's kind of, let's just say it's okay. 1, 2, 3, 1, 5, 6. I tried to make the numbers like not too horrible, right? So here's the thing. I could compute the determinant of this matrix using the algebraic formulas that I've given you so far. You know, I could pick a nice row or pick a nice column. Maybe the first column or the first row is looking pretty good to me. But here's another thing that the abstract definition gives you. So what happens when you add the multiple of a column to another column? Okay? What happens when you add the multiple of a column to another column? Well, here's the thing. In a matrix, let's say I'm computing the determinant of like V1 through, let's say I hit Vj, and let's pretend I have added to Vj the multiple of some other column. I'm going to call it Vk, but the rest are the same. So you can think of this as, you know, for example, I could subtract the first column from the second and third column to make them look a little bit easier, right? But the question is, what impact does this have on the determinant, right? What happens when we add some multiple of a column to another column, right? Because we know that determinants are multilinear, and we also know that determinants are antisymmetric, I can answer this question quite easily. Watch. So this becomes the determinant of the original matrix, you know, V1 with Vj untouched all the way through Vn, right? Plus alpha times the determinant of V1 through Vk Vn. Right? So this is just the determinant of the original matrix. This top one is just the determinant of the original matrix. But I want you to notice something. In this bottom determinant, Vk occurs twice. So for example, if I were to call these v1, v2, v3, right? And let's say I really want to subtract the first column from the second column in order to make my life easier. Hold on, let me move my face again. Okay. So let's say I want to subtract the first column from the second column in order to make my life easier. What's that going to do? So the first column stays the same, and the second column becomes, 0, 1, 4, right? 1, 3, 6. And so what have I done? I've replaced, this is still v1, but I've replaced v2 with v2 minus v1, and v3 is just v3. Hopefully that makes sense. So why don't I just do it in this specific example? So if I'm interested in computing the determinant of v1, v2 minus v1, v3. This is just as before, but I'm just trying to be more concrete now. v1, v2 minus v1, v3. This is going to equal the determinant of v1, v2, v3, which is the same as the original matrix. Yes, same as the original matrix. But this one becomes minus, because I can pull out the minus sign, the determinant of v1, v1, v3. Okay? I claim this one is 0. v1, v1, v3 is 0. Now, there are two ways to see this. You can see it geometrically, because v1, v1, v3 is a flat box, right? But another way to see this using just the abstract approach is these first two columns are the same, right? Which means if I swap them, that should negate the determinant. But swapping them doesn't change the matrix. So that whatever this determinant is, it's equal to its own negative because swapping does not change it. That is why this number is 0. Okay? So it turns out adding a multiple of a column to another column makes no impact on the determinant. Okay, that's a big point. So let me know if that makes sense. Because you get the repeat here, and I said swapping ought to negate the determinant, right? And yes, John Chesant, you're absolutely right. Swapping should negate the determinant. And because swapping should negate the determinant, but swapping here keeps the determinant the same, that means this determinant must equal its own negative. Because it equals its own negative, that means it has to be 0. So this gives you a very powerful and slick way to sometimes compute determinants. Because the determinant here is just equal to the determinant here. So guess what? This is a simpler and easier matrix, but you know what? I can do it again. I can swap the first I can subtract the first column from the third column and instead get 1, 1, 1, 0, 1, 4, and 0, 2, 4, right? And then I can subtract the second column from the third column, which is 1, 1, 1, 0, 1, 4, 0. I'm sorry, I should do 2 times the second column from the third column, which would give me 0, negative 4. So if I haven't made any computational errors, and I'll warn you guys, I'm extremely, extremely prone to computational errors, but assuming I have not, the determinant of this matrix is super duper easy to compute. It's just negative 4. Right? So knowing a little bit of the abstract properties of determinants really help you to compute them in a quick and painless and interesting way. So that's my overview of determinants. Oh my goodness, it took like an hour and 20 minutes to give you guys a brief overview of determinants. Okay, so now that you have a brief overview of determinants, I want you to form your own opinion about how painful you find them, and then we can continue. Thank you, Brian. And then we can continue to read Axler's paper and discuss. Let's read just like a little bit of Axler, because I know I sold you on reading that paper, so I don't want to not do it at all. So let's just read it for like 10 minutes, and then I might end the stream, because many people commented. Well, not many people. I mean, not that many people are commenting, but like some people did comment that maybe like an hour to 90 minutes was like people's math limits. But I mean, I'll be here again on Wednesday. You know. Okay. Just so you know, one more thing I want to say about this, just for your own general knowledge. You can do row or column operations. You can add multiples of rows to other rows or multiples of columns to other columns, and it will not have an impact on the determinant. And it's super powerful that you can do both row and column operations. Not all the row column operations, sorry. You can add multiples of rows to other rows, or you can add multiples of columns to other columns without having an impact on the determinant, which is a lot. That's a lot of firepower you can use to simplify a matrix and compute its determinant. So let's just go back to Axler now and read the first, just like the intro section, and then we can go back to reading the rest of the paper next time. So let's see. Let's go. All right. Let's go. All right, this paper will show how linear algebra can be done better without determinants. Brings a tear to the eye. So without using determinants, we will define the multiplicity of an eigenvalue. We'll define the multiplicity of an eigenvalue without using determinants. That's totally doable. I've seen that before. And prove the number of eigenvalues counting multiplicities equals the dimension of the underlying space. Okay, that's a little sus because I'm trying to think if I've ever seen a proof of that uses determinants. I'll look it over before I come again. But I actually think most proofs of this particular fact don't use determinants. Without determinants, we'll define the characteristic and minimal polynomials. This is very spicy. This I want to see. Because I can think of a way, but it's a lot of work. And then prove they behave as expected. Next, we will easily prove that every matrix is similar to a nice upper triangular one, turning to inner product spaces, and still without mentioning determinants, we'll have a simple proof of the finite dimensional spectral theorem. I'm sold. I'm very excited about this. A simple proof of the spectral theorem. I hope you guys are as excited as I am. That's very interesting. Determinants are needed in one place in the undergraduate mathematics curriculum, the change of variables formula for multivariable integrals. I'm trying to think if anywhere else in the undergraduate curriculum you use determinants. I guess Cramer's rule. I don't know what that is, LOL. The spectral theorem? Is that what you're asking about, can't commute? Let me know if that's the one you're asking about. I'm trying to think where else you use determinants in the undergraduate curriculum. You know, if you study geometry or if you study physics, I think you're probably using determinants a fair amount. And also, I guess like Cramer's rule and stuff like that. I mean, I'm not sure how often Cramer's rule comes up, but I mean, you do need determinants for that, right? Jacobians and Wronskians are all well, Jacobian. I mean, you use the Jacobian to do the change of variables formula for multiple. Oh, the spectral theorem is a theorem that tells you. It's actually an if and only if condition for when a matrix is, So determinants are used in quantum. Absolutely. Like if you're studying physics, you're definitely using determinants regularly. So I feel like this is a very, this claim is a little suspect to me, but I don't know. And in terms of Jacobians and Wronskians, like Wronskian is a fantastic one, actually. Thank you, Can't Commute. Like I wasn't thinking about differential equations, but yeah, you do. It comes up. So when you do the what's it called? Variation formula. Oh God, someone help me. Okay, I'm just gonna look it up real quick. Variation of parameters, right? The big fat variation of parameters formula. Like the one in like multiple variables, I think. There's Wronskis, there's determinants and stuff in that. So, okay, moving on. Thus, at the end of the paper, we'll revive determinants, but not in any of the usual abstruse definitions. We'll define the determinant of a matrix to be the product of its eigenvalues, counting multiplicities. Okay, so this is easy. This easy to remember definition leads to the usual formulas for computing determinants. We'll derive the change. That weird formula gives you back nice answers. I'm not sure which one. Are you talking about the variation of parameters formula right now? Can't commute? I'm not sure. So leads to the usual formulas for computing determinants. We'll derive the change of variables formula for multi-variable integrals in a fashion that makes the appearance of determinants there seem natural. Okay, I mean, I'm excited. Let's see what happens. A few friends who use determinants in their research have expressed unease at the title of the paper. I know that determinants play an honorable role in some areas of research, and I do not mean to belittle their importance when they are indispensable. But most mathematicians and most students of mathematics will have a clearer understanding of linear algebra if they use the determinant-free approach to the basic structure theorems. I mean, unless they're going into those areas of research, right? Then they're not going to be too happy about it. Let's keep on going. The theorems in this paper are not new. They'll be familiar to most readers. Actually, wait a second. I think someone asked what the spectral theorem was. I'm not sure if I answered the question. So the spectral theorem is a really powerful theorem that gives you an if and only if condition for when matrices are diagonalizable. So it turns out you can write matrices using different bases, okay? If you use a change of coordinates in the domain and in the range of like a linear transformation, if you use a change of coordinates, you can change the matrix that's being used. So you can redefine matrix multiplication using different coordinates if you change the linear coordinates you're using in the domain and in the range. And sometimes there's a way to do this to make your matrix a diagonal matrix. And diagonal matrices are super easy to work with because multiplying them is a joke, computing their determinants is a joke. So if you can do a change of coordinates to change your matrix into a diagonal matrix, a lot of amazing things happen. So for example, if you like differential equations, you might want to compute a matrix exponential. If your matrix can be converted via a change of basis to a diagonal matrix, doing the matrix exponential is super easy to do. Which, by the way, is how they solve systems of differential equations in your like standard introductory differential equation class. And so the spectral theorem gives you an interesting if and only if condition on when that is possible. When is it possible to change bases to rewrite your matrix as just a diagonal matrix? That probably came off as very vague if you've never heard these things before, but I hope that answers the question. So some of the proofs and definitions are new, although many parts of this approach have been around in bits and pieces without the attention they deserved. For example, in a recent annual meeting of the AMS and MAA, I looked through every linear algebra text on display, baller. Out of over 50 linear algebra texts offered for sale, only one obscure book gave a determinant-free proof that eigenvalues exist, and that book did not manage to develop any other key parts of linear algebra without determinants. The anti-determinant philosophy advocated in this paper is an attempt to counter the undeserved dominance of determinant-dependent methods. Okay, excited. This paper focuses on showing that determinants should be banished from much of the theoretical part of linear algebra. These are spectral theorem is similar to singular value decomposition. It is. The spectral theorem is stronger, though. So the difference is, thank you for the question, Hitoshi. So the difference is singular value decompositions are always possible, okay? If you have a spectral decomposition, you automatically get a singular value decomposition. It's better and it's nicer, but the disadvantage is it's not always possible. Whereas a singular value decomposition is always possible. But you can't do things like so singular value decompositions are obviously extremely important in like computer science and things like that. But you couldn't. I'm not sure you can exponentiate a matrix using a singular value decomposition. So like. It's not as useful if you're interested in solving differential equations and whatnot. But singular value decompositions are, I guess, like a consolation prize when you can't do a spectral decomposition, because you can't always do a spectral decomposition. There are a number of these interesting consolation prizes throughout. So for example, Jordan normal form is another really interesting consolation prize in the situations where you can't do like a full-on diagonalization. So I hope that answers your question, Hitoshi. Thank you for it. So Brian says, I will say from his book, I really like going through proofs with no determinants as a supplement. All right. Well, I feel that. I mean, I did my best to give you guys like a brief overview of determinants, but I'm not going to pretend it's not a lot. So... All right, determinants are also useless in the computational part of linear algebra. I agree with that. For example, Cramer's rule for solving linear equations is already worthless for 10 by 10 systems, not to mention the much larger systems often encountered in the real world. This is true. I don't think anyone's using Cramer's rule to solve for anything. But Cramer's rule is of immense theoretical importance, I feel like. In a field, if you have a basis, then you can write each element as a matrix, determinant as a norm function. If you have a basis, you can write each element. In a field, if you have a basis, then you can write each element a matrix and the determinant as a norm function. Yeah, that's I forgot about that. Thank you, John. I'm not going to be talking about that at all here. But thank you for the comment. So I guess oh my goodness, I'm going for so long, but it's just exciting. I don't know. I like this stuff. So what is Cramer's rule? How many in the chat know about Cramer's rule? It's very interesting. I feel like I need to defend it because it's being maligned right now. It's getting a lot of hate. So I have to defend Cramer's rule for a hot second. So also my face is in the way again. Let me get out of the way. So Cramer's rule is a formula that involves determinants. Okay, so Cramer's rule is a formula that involves determinants. I'm not gonna. It's like a 10-minute derivation, but like I said, I'm trying to be respectful of people's like math capacity. But it's kind of interesting. So like, let's say you have a linear system of equations, right? So I don't know, like let's say it's x1 minus 2x2 plus x3 equals 7. And then I don't know, 3x. I'm making this up, so I should probably make it up faster. I don't know, a system of linear equations, okay? Normally, if you were to solve this system of linear equations, you would row reduce. I put up my first like Math with Friends Linear Algebra 1 series if you want to watch it, if you've forgotten how to row reduce. But normally that's what you would do, right? You would row reduce this matrix, and you would use that to solve for x1, x2, x3, and of course there are possibilities. You can get infinitely many solutions, you can get no solutions, or you can get a unique solution, right? But the weird thing about Cramer's rule is it actually gives you a direct formula. For example, let's say you were only interested in what is x1. I don't care about x2, x3. I just want to know what x1 is. And Cramer's rule gives you a direct formula for what x1 is using the coefficients. And when I say formula, I mean like the quadratic formula or something, So Cramer's rule gives you a formula directly giving you the answer for a variable of your choice, which is, I mean, I don't know. I think that's kind of cool. And it's a very complicated formula. It involves not computing one, but two determinants for each variable that you're interested in. So I'm not going to pretend like the formula is like computationally fun or easy to do, but it has like immense theoretical importance. I mean, even just knowing that there is a formula you can use in many circumstances to directly give you the answer for any of these variables. I mean, that alone is very cool. And, you know, for example, if you like working with matrices of polynomials or something like that, or if you're doing something a little bit fancier, it's nice to have something like Cramer's rule that gives you a direct formula, because you can study the properties of the situation you're in. You know, it's like having the quadratic. You may not always use the quadratic formula to solve quadratic equations. Maybe you think it's like too complicated sometimes to pull it out. Like if you can factor a quadratic directly, obviously always do that. But sometimes you can study the type of situation you're in using the quadratic equation. And I would say that's what the importance of something like Cramer's rule is. That's the importance of having a direct formula for these variables, even though admittedly it is a little bit of a nasty formula. Maybe I'll talk about what Cramer's rule is next time. But let me let Axler finish hating on it first. So determinants are also useless in the computational part of linear algebra. For example, Cramer's rule for solving systems of linear equations is already worthless for 10 by 10 systems. That's how you know this paper was written a while ago. I guess computers were not as powerful back then. But I don't disagree with the point that's being made here. You wouldn't use Cramer's rule to actually solve the linear system. Like row reduction is way faster. But I think they teach Cramer's rule so you know there is a formula, because the knowledge that there is a formula and the like shape and scent of this formula comes in handy. Okay. Many computer programs efficiently calculate eigenvalues numerically. None of them use determinants. That's true. I mean, to my knowledge, that is true. To emphasize the point, let me quote a numerical analyst, Henry Thatcher, in a review. Okay, I find it hard to conceive of a situation in which the numerical value of a determinant is needed. Cramer's rule, because of its inefficiency, is completely impractical, while the magnitude of the determinant is an indication of neither the condition of the matrix nor the accuracy of the solution. I actually think it'd be fun to talk about condition numbers next time, because I know all you computer science peeps out there would really enjoy a short discussion of the condition number of a matrix. But in any case, I'm gonna stop this here. Thank you to all of you who decided to show up. I really appreciated it. And you know, the last stream that I did was my first stream, and I already feel a little bit more comfortable doing it. So I have a feeling the quality of these streams is going to improve as time continues. And I do want to thank you guys for showing up. And other than that, yeah, I don't know what else to say. I'll be back again Wednesday at 1 p.m. I'll also be dropping other videos occasionally. There's a couple of like math art projects that I'm working on the side, and I'm excited to share those with you guys as well. Thank you so much to all of you guys, and see you on Wednesday. All right, peace.